everybody. Hello again. I'm Steve Greenberg. I lead developer relations for Earth Engine.
Hi, my name's Daniel. I'm tech lead of machine learning in Earth Engine. I've been on the team for about 7 years now.
Awesome. And you are at Geospatial Machine Learning, an introduction. So this is our first session at G4G focusing on machine learning. And during this session, I'm going to start with an introduction to machine learning for about 10 minutes that does not assume any prior knowledge, just to get us all on the same level. Then I'm going to hand it off to Daniel, who will give you an overview of the various approaches that you can use to doing machine learning in Earth Engine with geospatial data. After that, we're going to talk about some best practices, some tips and tricks that we've learned on the team for getting the most value out of machine learning. And then we will talk about navigating the rest of this conference, because this is actually the first of 5 sessions that are focused on machine learning. All right. So first, why should machine learning matter to you? People like you in organizations all over the world, nonprofits, researchers, governments, you want to understand the landscapes around you to make changes that positively impact those landscapes. You might, for instance, want to count the trees in a forest. And this model that I also mentioned during the plenary session this morning was built by a team at the University of Copenhagen. And it uses a fully convolutional neural network to count trees, count individual trees. Or you might want to segment the fields, identify each individual field in Iowa. Sean Woltman from our sales organization recently demonstrated how to do that using Facebook's Segment Anything model. And you can take this map of Iowa, and you can segment out all the fields as individual fields. Once you have the field segmented out, you can do zonal statistics and sort of gather information about every field. You can accomplish this with a deep learning network like Sean did. You can also use the SNCC, simple non-iterative clustering algorithm that's built into Earth Engine. Or you might want to detect damaged buildings after a natural disaster, like an earthquake or a flood. So Google's research team did this work. And this is actually 2 machine learning models in one to accomplish the solution. The first model detects the buildings. It's called object detection. And once each individual building is detected, we use a second model to classify the building as either intact or destroyed. And if this all sounds sort of abstract, I'll say that this is the kind of model that can make a real difference in the world, because it allows emergency teams help to arrive at a location in hours rather than weeks. Of course, the most common geospatial machine learning task is to classify the land. Land cover is the observed physical cover of the Earth's surface, and it describes what's vegetation, what is urban built-up area, what's farmland, etc. So that distribution is called a map. And so we take the imagery that you get from a satellite or other aerial imagery, and then we turn the pixels into a land cover map. And let's say we want to do this at scale. Let's say we want to do it over the entire surface of the Earth, over a time series spanning many, many years. Once you have that, once you have maps developed for a set of imagery, you can start to do things like understand deforestation, or changes in cropland, or changes in carbon emissions. So being able to take imagery over time and derive a map from it turns out to be incredibly useful. So that answer to that question I initially posed of why should you care about machine learning is that it is a tool that allows you to scale your understanding of the landscape, which is incredibly valuable for making progress against the mitigation, adaptation, and protection goals that we talked about this morning. At this point, I'd like to zoom out and paint a broader picture of artificial intelligence and machine learning. These are topics which are in the news a lot these days. AI refers to the overall work of developing computer systems which are performing tasks that typically require human intelligence. And machine learning is a subset of AI. It's a subset of AI in which the systems learn without following explicit instructions. Now, we know that large language models like ChatGPT and Bard are really important. And we actually do have a session to discuss large language models on Thursday, which I encourage everybody to attend. But that's not what this session is about. This session is focused on computer vision and machine learning within the Earth observation sphere. I want to talk a little bit about sort of the ways that machine learning can be classified or characterized. You can divide machine learning by the type of the data that you're operating on. So you might start out with machine learning operating on databases or spreadsheet data, so-called tabular data. Or you might have machine learning on audio input, or to do translation, or text, maybe even large bodies of text, maybe even the whole text of the internet. Of course, many of the folks in this room work with satellite imagery data. And that's what we're going to focus on today. Machine learning can also be characterized by the amount and the type of supervision that the model gets. In supervised learning, you know what your outputs should look like. You have so-called labeled data that expresses what you believe to be the desired answer, at least for a subset of the data. Like an example of a supervised learning task is classification. Is this email spam, or is it not spam? Is this point on the Earth an urban area, part of the ocean, cropland, etc.? Another task of supervised learning is regression. Regression is predicting a target value. So how much should I bid on this item in eBay? Or how many trees are located in this particular area? So that's supervised learning. In unsupervised learning, you don't give the model a sample of answers. Instead, you ask the model to tell you what it can learn about the data. Unsupervised learning is really great for exploratory analysis. You might throw a clustering algorithm at a set of data and ask the machine learning model to tell you what are the natural clusters of the data. And for completeness, there's also semi-supervised learning where you have partially labeled data, and reinforcement learning where you have an agent that learns about what the best choices are to make. We're not going to go into too much of those today. The third way to sort of think about machine learning or separate it out is to just think about the structure of the model. Deep learning uses artificial neural networks that mimic the way the human brain works. Deep learning can be incredibly powerful. It can also be computationally expensive. So for completeness, we want to give you a full tool belt, to tackle machine learning. And so we're also going to talk about classical machine learning methods, which utilize less expensive model architectures. So this is sort of the "you are here" slide for today. We're going to be focused on satellite imagery, talking about both supervised and unsupervised learning. And we're going to talk about both deep learning and classical machine learning. Let's talk a little bit more about how machine learning works. It's actually fairly similar to traditional programming. So in programming, you typically have some information, and you want to get an answer out of it. And in traditional programming, you put a human being in the center. The human being codes up the approach to turning raw data into an answer. And in machine learning, we kind of do the opposite. We basically provide a set of answers and the information, and we let the computer put together the recipe. And in machine learning, we call that the model. The model is the recipe that we derive to make decisions. And there's two other concepts that I quickly want to define for folks here. Training data are the examples that we provide to learn from. And the characteristics of those examples are called the features, the predictors that we use, the characteristics of the data to make decisions. Every machine learning workflow kind of follows a set order, which is the following. First, you decide on your inputs and outputs. What's the answer that you want to get from the model? What's the data that you have to go into the model? Next, you gather a set of training data to feed into the model. You select a model architecture, an approach. There are a number of different approaches for training machine learning. You select one to use. You apply that architectural choice to your training data, and then you get a model out. Once you get the model out, you then use it to predict on new data, and you can assess your accuracy. And if you're not happy with your accuracy, you go back to the beginning and start again. Gather new data, try different model architectures, rinse and repeat until you're satisfied with the result. So let's talk about land classification and just kind of go through this order here, this process, and explain how it could work. So first, you need to decide on your inputs and outputs. Let's say we're working with Landsat data. So what we want to do here is classify each of the pixels in this map as belonging to one of three classes: vegetation, water, or urban area. So those three classes are our answers, and the features that we have are the features of Landsat. OK, so we want to get vegetation, water, and urban areas out. And the data that we have is from Landsat, so we have 6 spectral bands to use. We have 6 features that we can apply to the model. The next thing we want to do is get some training data to work on. And this is actually like some incredibly cool functionality that's built into Earth Engine that just makes things easy. You can pull open the code editor and drop some points on a map and classify. And that's what we've done here. We've basically taken some red points, dropped them in the urban center of San Francisco, some blue points, dropped them in the bay and the ocean, and then some green points and dropped them into sort of vegetative areas. And once you have these training points that you as an expert have said are true data, this is your training data, you then grab the features for them, the Landsat values. And you need to select a model to work with. For simplicity's sake, we're going to say there's only 2 bands, x and y, and only 2 classes, just to make the next few slides really easy to draw and easy to make sense. So you've got two x and y bands here, and you've got vegetation area in green and urban areas in red, and you want to separate them out. So maybe you'll draw a line like that and separate out the 2 classes. And any new points that fall above the point are classified as urban areas, and if they fall below the point, they're classified as vegetation. This actually is one of our classical machine learning approaches. It's called support vector machines. And it really highlights the importance of why it's important to have good training data, because if you have training data that's not representative, that line is not going to be in the right place. There's also other different kinds of algorithms. Decision trees don't just use sort of a straight line. Instead, they use a set of decisions. Daniel will talk more about this. Neural networks support more advanced and more complicated decision making. But once you've chosen your model and trained it, you have a line. And the line is drawn. And then once new data comes in, you classify it. So a new point comes in, and the point is there. So this is going to be classified as vegetation or urban. Anybody? Thank you. Vegetation, exactly. So the new point's below the line, so it's classified as vegetation. And once you've got the model, you can then apply it across the entire area that you're looking at, in this case the Bay Area, and get your predictions out. And assess the accuracy. How many of the new points are accurately classified and how many are inaccurately classified. So we're left with our final step, assessing the accuracy of the model and repeating the process if we're not happy with the accuracy. So that was a simplified approach. Folks, I'm sure there are folks in the room who have done more ML training and understand train test splits and hyperparameter tuning and things like that. We will get into that over the course of this week, but I wanted to start with a very simple example. And there are a bunch of reasons that machine learning models can go wrong. They can go wrong because you have bad data. Your data set is too small. It's not representative. It's noisy. It might be polluted with irrelevant features. So figuring out what's the data that you want to train on and what are the features you want to use to train on, what are the characteristics, the predictors, that's really critical. You also might have a model that doesn't work well. Maybe the model doesn't generalize well. It might be too simple, or it might be actually too complex and kind of overfit the data. And either one of those will lead to bad results. And so getting the model to sort of that Goldilocks spot in terms of complexity is very important. So this is sort of a theoretical overview to machine learning. And in the rest of the session, Daniel is going to be talking about how you actually do this using Earth Engine and other tools. So I'll hand it over to Daniel.
All right, thank you, Steve. All right, so let's go ahead and get started. And we'll start with classical machine learning and Earth Engine. Maybe I just want to get a feeling, how many of you have done any machine learning or have used Earth Engine to do kind of land cover classification? OK, great. There's a lot of people who've already done this sort of thing. So if you're one of those people who are interested but you don't know, maybe you got an idea, maybe someone you can talk to afterwards. So let's go ahead and get started here. All right, so classical machine learning. Essentially, it's not neural networks. That's the main point. But typically, classical machine learning are algorithms that are based on simple rules. They're typically older, and you can sort of peel back the front layer and sort of look into what's going on in the inner workings. You can usually describe them as a simple set of rules, and there are some examples. We have regression, which is basically fitting a line to some points. It's a little more complicated than that, but that's essentially it. We have support vector machines, kind of like Steve was talking about, where you say you want to align and things above it are one class and things below it are another. Another example is a decision tree, where you basically just have a bunch of if statements on your inputs to the model, and then depending on the algorithm there, you get one thing or another. Okay. All right. So how do you do that in Earth Engine? Well, for our supervised learning, we have a lot of these algorithms under our EE classifier like object or methods. Our EE classifier methods support classification, which is I want to figure out what category is this prediction fit into, and regression. Basically, I want to get a value that's maybe a number, and I want to get observable of something like imperviousness to water, something like that. In Earth Engine, it's actually extremely simple to do supervised learning. Essentially, our API is built around having train, where you have a bunch of training data, and classify. We basically make the classifier do predictions, and that's it. There's quite a few example algorithms, but just to name a few, we have random forests, KNN, and spectral region, and you see this SMILE prefix. That's just because the underlying implementation uses the open source SMILE machine learning library. So that's, if you're wondering how did we do it, that's part of it. For unsupervised learning in Earth Engine, we have quite a few offerings, and they're not all categorized under the classifier object. So in this particular case, we have a bunch of algorithms under cluster. We have a lot of things from Weka, so Weka k-means. We also have regression under both EE reducer and some specialized algorithms under image segmentation and temporal segmentation. So on the image here on the right, in the top right, we see just kind of like black, white, gray. That's just automatic clustering of some radiance values from some top of atmosphere from Landsat. That's really useful if you want to just get a feel for if there's any potential patterns in data and you don't really have a starting point. That's a good place to sort of get some initial insights from. The bottom picture here is just showing a fit, basically using the using the continuous change detection algorithm, CCDC, to basically over a piece of land, essentially it's like, has this sort of land changed its use over time? And it's very good if you have seasonal variations, because the crops might do something normal and then all of a sudden you have a grassland, so it's not crops anymore, so the seasonal variations will change. So there's all kinds of tools that we have for unsupervised learning. So you may be asking yourself, why would I even want to use a classical machine learning model? All the new stuff is using deep learning, TensorFlow. Well, here's a few really, really good reasons. One of them is that it's really easy to get started. With Earth Engine, we built in a lot of these classical machine learning algorithms, so it's essentially just a few lines of code to actually get started. And there's a lot of examples you can adapt from. So there's a lot of literature and things to sort of support you in your journey of trying to solve problems. The second, and is also a very important point, is that classical machine learning algorithms are very understandable. So it's pretty easy to kind of look at a decision tree and say, okay, because the radiance value was over 0.5 here, it falls into this category. Or you can sort of walk along and understand what's happening. When you have a deep, a neural network, you might not know what is this third hidden layer doing, and it takes a lot of expertise to even understand what's happening there. So it's also easier for citing things, and if you are encountering a problem or you have biases or something like that that you really want to figure out, understanding the model is actually really important. And the last point here is you actually can get pretty good results. So using something like random forest, you can publish your paper and actually get work done, and you don't have to spend a lot of time figuring out, I gotta learn this whole new library and deploy this thing, and I gotta, it's a headache to do deep learning sometimes. And it's a really good starting point. So if you're doing your analysis and you're using classical machine learning, and it's a kind of a good place to just get a baseline and then build from there. So I'll go ahead and walk through a simple example. This is based on one of our Egypt classification examples that we have available in the code editor. So the goal is we just want to make a land cover map, slightly higher resolution than what we want to use our labels from, over a region of interest. So let's go ahead and talk about the data that goes into the model. So for this example, we're going to be using a MODIS data set, MCD12Q1 for class labels. I think this is basically some land cover classification. But the thing about the MODIS data is it's at 500-meter resolution, so that's relatively low resolution if you're talking about things over neighborhoods or cities or even crops, like over patches of crops and things like that. For the model inputs, we're going to be using Landsat 7 imagery to sort of build our model on. It's arbitrarily chosen, but you can use Sentinel, figure out what data kind of makes sense for your region and the temporal needs that you have. And then to build the training data for the model, we're going to randomly sample in a region of interest, essentially different band values, and then we're going to use the input label from the MODIS data set and merge it together into a single image collection, and then sample that to turn it into a table of data. So on the right here, you can just see this is essentially the Earth Engine code to do this. So the most important things to take away from this is that we basically have our image collection. We do a little bit of filtering. We have our Landsat imagery, do some filtering, combined it. And also at one point, we're making a composite just because we want some cloud-free imagery. You probably would want to be a little bit more thoughtful about how you're going to build a composite for your training data to your model. But for this example, we're just going to use the off-the-shelf simple composite algorithm. And you sample your data. So the next important step here is that we need to pick a model, and then we need to actually train it. So in this example, we're just going to pick the SMILE cart algorithm. Again, SMILE is just a library that we're using, and CART stands for classification and regression tree. So we're just going to have a single tree that we're going to do classification with. And in order to train your model, all you need to do is basically have the train method and then put in your training features, and that's essentially it. You can actually see the details of what the trained model actually is by using the explain method. So this would print you just a bunch of information in the console. It'll tell you basically what is the model doing. These are the splits and all that stuff. So it's very easy to get an idea of what's happening behind the scenes. So the last step is actually getting your upsampled land cover classification. So in Earth Engine, it's really simple. All you need to do is do your input imagery, which is this Landsat composite. Then you just use the method classify and the classifier that you just trained. And then the step that's probably one of the most important is you actually want to verify the results of the model you trained. So even though you got your cool upsampled imagery, your upsampled land cover, what you should do is you should have some ground truth labels or some sort of validation data set. And then what you do is you compare the predicted values to the validation data set. So we have a very easy method to do this. It's error matrix, which gives you a confusion matrix, and then you can compare with that to see how well did my model do versus the truth. And then from there, you can do some things like you can say, oh, maybe I need to use a different model, or maybe I need to have more trees, or maybe something's wrong with my input data. But you can't know unless you actually verify. So here's the results. So this is about 30 lines of Earth Engine code. And you can just see based on this, on the picture here, it is amazing. You can get upsampled 30-meter land cover with essentially little to no work. This is essentially an example that you can adapt. And this is a great starting point if you don't even know where to begin for solving certain problems. That sounds all great, but there are definitely limitations. So Earth Engine has a fixed number of models built in. It takes a lot of work to build them out, to maintain them, and it's not easy for us. Also, a lot of people can do really cool, cutting-edge things using machine learning libraries outside of Earth Engine, like PyTorch, scikit-learn, TensorFlow, etc. So that's one drawback. You're going to have a limited selection of models you can actually use. The second one, and it's probably one of the most frustrating ones, is that you can get really decent results, but then you want to scale it up and get more training data, or you want to make your model bigger, and then I'm getting memory limit exceeded. There's a finite amount of memory that you can put into an Earth Engine model. So it's about 100 megabytes in terms of the training data of the table that you can make. You have 5 minutes to actually get that classifier trained before your request will time out. That's not really fun. And then there's also some other limitations, I'm sure. I think there's 32 megabyte limit in terms of the string sizes of the tree classifiers. That's not fun. One thing I am really excited about is that we're working really hard on launching save classifiers. So that will work around some of these limitations. You'll have much bigger size and training data, and the 5-minute limitation will go away. But that's coming soon, so listen for an announcement, hopefully, at some point. And then the last point is that Earth Engine models are not specialized for any particular problem. So I think as we saw earlier today, that certain deep learning models are able to give you more accuracy, or they're more tuned to specific inputs or multimodal inputs, or you want to actually generate patches of imagery. So what I'm trying to say is that it's essentially limited. So deep learning is how you unlock some of these capabilities. So how do you do that in Earth Engine? So before I kind of go into that detail, I just want to review what do I mean by deep learning. Essentially, it just means a neural network that has more than one hidden layer. But I think just for convenience, I'm just going to mean anything you do in TensorFlow or PyTorch or outside of Earth Engine, that's going to be deep learning. Right. So why would you even use deep learning? So, like I was saying before, deep learning is a flexible framework with all these different types of machine learning libraries, and it handles multi-dimensional data very well. What does that mean? That means if you have an image, it can learn from the entire context of all those pixels. So let's say you have a shape of a building, and it can actually learn something about the arrangement of pixels. So you can get insight than you would typically get from these built-in machine learning models in Earth Engine. And that's really relevant for geospatial stuff, where you can get a lot of information based on just what you see in terms of grouping of pixels. And then the other very important one is that deep learning is really good at learning from time series data. So if you have a video, you can think of it as learning from video, but generally machine learning is super good at tackling high dimensional data. And that's extremely relevant for Earth observation, where you have multispectral imagery. You have sometimes 10, 30 bands, maybe even more. And then you have a time series to deal with, and then you have to deal with patches of pixels that you could possibly learn from. So all of this points to deep learning as being a great solution. And on top of that, deep learning is really specialized to being trained on very large amounts of data. So ChatGPT didn't train itself. It essentially downloaded the entire internet in order to train the model. And so these frameworks that these models are built with are specifically designed to handle large volumes of data. And in addition to that, a lot of these models have a lot of parameters and need even more data to get better and better accuracy. So sometimes it's orders of magnitude more data in order to improve the accuracy of the trained models. So you're not going to be able to do that in Earth Engine, unfortunately. And there's even more reasons to use deep learning. For example, solving intractable problems where you don't even know where to begin. The model can just learn things, and it's magic, essentially. The other part is that if you want to deploy or you're sharing your model, it's a lot easier to do that outside of Earth Engine. And then the last part, and this is one of the most important ones, it's very easy to adapt existing models to solve new problems and to be trained on new data sets and to predict things that you care about. So how do you do this with Earth Engine? So before I kind of go over all of that, let me just talk about the life cycle of a deep learning model. So you have to get all your data, those large stack of hard drives essentially that you need to get it all first. Then you kind of have to architect the model that you kind of want to work with. And then you train it and evaluate. And at this point, you kind of determine, okay, do I need to tweak some things? You might do some what we call hyperparameter tuning, but it's essentially just saying, I'm going to change some things about the model. Or maybe you have to re-architect the whole thing from scratch. Or maybe you have to get entirely new data. I don't know. But the point is, this life cycle is you're going to do this cycle of building, training, and evaluate. And then when you're done, you do your predictions and hopefully materialize something as a map of some sort. But where does Earth Engine fit into this? So Earth Engine is a key player in terms of getting the training data out from the cloud. It's also in terms of generating those predictions and also for visualizing the data. So Earth Engine has quite a few APIs that we've talked about, and we are investing more in getting training data out or just data extraction. And then with our connector to Vertex AI that we're building out, you're able to do predictions directly from the model that you've trained and uploaded into the cloud. And then last, you can visualize that map or those predictions, and that's pretty much your problem is solved. So to review, extracting data with Earth Engine, I would recommend using get pixels and compute pixels. It's better for getting smaller patches of imagery. The export methods that we have are very good if you have like large images you want to get out, but they take more time because it's a long-running task. The other thing to note is that deep learning models expect a very generic sort of data type. It's tensors, essentially a fancy name for an array of multiple dimensions. And if you're going to use get pixels, then try to maybe to save yourself a conversion step, you can extract them as NumPy arrays or something like that. And if you have to use our export and import flows, I recommend using TF records, just potentially one less conversion step that you have to do. And after you get all your training data, you actually have to build the model. So getting the inputs to the model is a little tricky. If you have a time series, you need to say how, it could be many deep. You have to get the shape right with the number of pixels, and you have like a lot of bands. So, it's a little tricky actually trying to get the model to take the remote sensing data and then to convert that into an output that's actually usable. So this is the part where I recommend you go to the neural networks talk. That's going to be tomorrow. You're going to get a lot more information on actually how to do this and walk through an example. And then once you've trained your model, you essentially can just upload it to Vertex AI. You may need to upload it in a storage bucket somewhere, but that's pretty much it. And then to actually get predictions, we have the method ee.model from Vertex AI, and very similar to the classifiers that we had before, you have your input image, and you just do predict, and then the model, and then you get results. That's kind of what we want to make it really easy. However, there are still a lot of challenges, especially with deep learning. So I really want to emphasize that it takes a lot of domain knowledge to build and understand and even use these models. So what do I mean by that? Like to know how many layers am I going to actually need, or what kind of input do I need to get to put into that model is actually extremely difficult to understand. I recommend trying to find other examples or simple things that you can sort of kind of start with to kind of guide you there. The other really important thing in terms of domain knowledge is input data. You have to make sure that your input data is not biased or somehow not oversampling certain things, and your model will learn like every little, like especially a neural network with a lot of parameters can pick up like really weird features that you didn't expect. So I would say definitely try to understand what you're trying to build your model with. And then the last part is understanding. So even if you train it and everything like that, it's hard to even just know, okay, what's happening on the internals, like why is this node firing? It's a challenge. The other part is that it's very expensive and takes a lot of time to actually fix some of these problems. So you might need to rewrite or retrain your entire model. You might need to extract all the data all over again. So yeah, that's a gotcha for deep learning. But hopefully, I'll give a few tips on how to avoid some of these sharp edges when it comes with deep learning. So first, use an existing model when applicable. So like I was saying, building a good model from scratch is extremely difficult. And someone might have already done it, or at least something very similar to the use cases that you have. And then what you could do is you could retrain the model on maybe the data that you have, or maybe to learn some output features that you're interested in or something like that. And that is probably a lot better place to start than just trying to come up with something from scratch. And then the other point why you'd want to do that is that failing faster is just better. Because if you try to use an existing model, it doesn't work for you, you've learned something and you've made progress. If you are just trying to do this from scratch, you can invest a lot of time in order to just find out, okay, what I'm doing is the wrong approach. Another really important point is overfitting. So I was talking about earlier, you have to really understand your input data. Well, one of the reasons why is because if you don't have a representative sample of something that you're trying to make predictions from, your model might work really well in the area that you trained it. So I trained the model to categorize land cover in Chicago or something like that. Now I want to apply that same model to something like New Zealand. Oh, wait, it's like not accurate at all. Well, it's because now you're trying to reapply what you just trained to totally new space. And if you wanted to do something globally, either you train on global data or you have to retrain it with a smaller subset and do some sort of low shot kind of like modeling. So yeah, be aware of that. And the other thing that I think is really important is that if you can try to have less parameters, this is both applicable for both deep learning and for classical machine learning. So here you see on the right, there is a chart, and we have a magenta line that is kind of wiggly, and it's going through all the blue dots. And this is our training data, and this is some hypothetical model that we use regression with, and it fits perfectly, right? Well, it's actually not necessarily a good model because it's overfit to all the data. Why? Because when we have new data coming in, our validation data set, you can see that it strays quite far from the magenta line. And in this case, if you had a simpler model, just as a parabola, basically could be explained by like one or two parameters, that will actually do a lot better for larger like sets of data and things like that. So sometimes using less parameters is better, sometimes using smaller weights is better, but it takes a lot of nuance because say you have a deep learning model and you have something that is underrepresented, but it matters to you, then you have to weight that more. So these are things that you have to think about. And then on that note, data is definitely everything. So here's a few tips to help you kind of avoid some other sharp edges. So one thing is you might want to normalize all the training data to your model. And the reason why you'd want to do this is for things like gradient descent and just some other deep learning techniques. If you have large variability in one variable, like your band 1, but band 2 is like really small. It's like goes from 0 to 1, and band 1 goes from 0 to a million. When it's trying to optimize what parameters should have certain weights, it might spend a lot of time trying to optimize one dimension, but not being optimized in the other. So that's one thing that I definitely recommend. The second thing is to understand the quality of your labels. Not only that, but not every expert or not everyone's going to agree like, oh, this is a wetland or this is a marshland or something like that. Like this, trying to understand what decisions were made and if there's going to be certain labels that are going to be kind of debated, sort of like understand that. So yeah, I don't know. There's a lot that goes into that. And then the last one is be careful with composites and just in general with imagery in general. So for example, how many of you has used Sentinel-2 imagery at all? A lot of you. So, but did you know that if you just try to use every single scene of like Sentinel-2 imagery, you're going to get double counting on some of the edges because they try to make this data product to be gridded in certain cells, but then there's a little bit of overlap sometimes with some of the imagery. So you have to be really careful when you're taking that data and trying to train a model because there could be statistical things that are kind of weird, like this double counting, or if you're using a composite, you might be getting cloudy pixels, and then that could really screw up your model. So you have to be really take the time to understand what's going in. All right, so I think with that,
Sure. We're going to talk about the rest of the sessions, and then we're going to answer any questions you have. Maybe it's a good idea, we can go through this, but also we can turn on the mics and start thinking about your questions. We've got some time.
Yeah. So if you want to learn more about classical machine learning, I recommend going to Noel's Machine Learning with Earth Engine's built-in classifiers. I think that's going to be in this room right after this. So definitely check that out. If you want, during this time, the next time slot, if you want to learn more about how to just do large computations in Earth Engine, then there's going to be a talk on that using Earth Engine for very large computations. So that's something to look out for today.
Yeah, in particular for folks who are quite experienced with Earth Engine, that's brand new content from Mike Dixon, and I think it'll be very interesting, sort of a peek behind the curtains as to how Earth Engine scales.
Yeah. And tomorrow, that's where we're going to get into the real meat and potatoes of some deep learning. So neural networks 1 and 2. I think that's going to be hosted from Nick and Genna.
Nick and Genna, yeah. There's enough neural networks content that we decided to host 2 sessions on it with Nick and Genna, sort of taking you through some of the latest work that they've done. So really exciting.
Yeah, and there's a lot of other hands-on EE too. So if you're already familiar with deep learning and you want to say, learned some tricks with Python or figuring out how do I scale my data ETL, like getting my input and output data from Earth Engine, then check out either the extending Earth Engine with Python, with GEmap, getting data into and out of Earth Engine also. And then I think the last one is just a general data analysis, GIS 101 in EE. So some hands-on classes to look out for tomorrow.
Noel's teaching Earth Engine scaling and debugging on Thursday, which is another class that's sort of tailored for folks who've got some experience with Earth Engine, might be hitting some problems and want some advice on moving past those challenges. And then there is a session talking about LLMs. It's, at this point, a discussion session. We don't have a big announcement about LLM integration in Earth Engine that we're bringing this week. So it's a discussion to sort of talk about how we believe LLMs can impact the work that we do.
All right.
Great. Yeah, at this point, we are available for the next 15 minutes for any questions that you all have. Please feel free to use the microphones there. And yeah, Danny, we'll take the questions.
Yeah.
Thank you.
Thank you.
Awesome. Thanks for getting us started.
We got a question up here on the right. Okay,
Yeah.
thank you.
Thanks for the talk. It's really useful. You mentioned it's better often to use existing. Can I make this taller?
Yeah.
To use existing models where people have done similar stuff that you want to do beforehand, so you don't have to build the model yourself. Is there anywhere that you'd recommend where you can find resources on that or existing models, or are you just looking through published papers and that kind of thing?
I'm unfortunately not the domain expert in trying to tell you where the models are. That's something that we're both thinking about.
Yeah, I would say there's a couple of things. You sort of need to choose initially whether you're thinking about deep learning or classical machine learning and make that choice up front. If you're looking at classical machine learning, I would say that we do have a bunch of examples on Earth Engine's developer site that are like a good place to start for general techniques. If you're looking for sort of more deep learning models, I think your published paper idea is a very good idea. That I talked about how Nick found that the model for counting trees, and that came directly from a paper. And he was able to just literally, the paper, not every paper does, but that paper happened to include a link to the model on GitHub, download the model, pop it up onto Vertex, and just get predictions easily. There's also the model garden. So TensorFlow has a model garden that's public, and that's a source of taking a look and finding existing models. That's, for instance, I talked this morning about where Sean Woltman found the segment anything model from Meta. That's a place where you can find those models and download them and get them. So there are places where you can sort of search and find existing stuff.
Yeah, thanks for your talk. Just a quick question regarding Vertex AI. So is that limited to TensorFlow only, or can I train a model locally, upload it, and start predicting?
That's a great question. So it's very flexible, actually. You could train your model in PyTorch or scikit-learn or whatever. Vertex AI has a bunch of container images that contain the libraries that you need pre-built. And what you could do is you could train your model and connect that with Earth Engine. Now, we made it really easy with TensorFlow right now. You might need to add a little bit of wrappers to get, say, PyTorch or some other framework to work. But right now, we're actively working on making that easier. So we're going to have really easy PyTorch integration and other machine learning frameworks available. So yeah, just to reiterate, Vertex AI is super flexible. You can have pretty much anything, and you can have custom containers too. So
That's right.
yeah.
Right, so you don't have to train the model in Vertex AI. You can
That's right.
import it using like Docker or something, right?
Yes.
Okay, cool.
Yes. Yeah, Vertex AI really has, it's an umbrella product that actually has quite a lot beneath it, but it has a training product and then also a product for hosting models for prediction.
Yes.
Yes, and you don't have to train in Vertex to host in Vertex for prediction. Of course, yeah. What other questions do folks have?
I was wondering, so a lot of the demonstration was in the JavaScript API. And I was wondering, what are the like EE classifier or these other types of algorithms, are they available through the Python API as well, or would you just basically, I don't know, use other Python libraries like scikit-learn, et cetera?
That's an excellent question. Yeah, so I want to be very clear. All the built-in Earth Engine classifiers you can access from Python or JavaScript. It actually doesn't, it's language agnostic. It's all server-side. So whenever you see EE.something, it's usually an algorithm that's actually hosted in the Earth Engine backend in the cloud. So that's one of the reasons why it's so easy to use. You don't have to install that third-party library and like, oh, this needs a bunch of dependencies and whatever. No, you can just use the algorithm pretty much exactly the code I saw in JavaScript. You can pretty much translate that to Python and it would work. But, yeah.
If you do want to use scikit-learn or XGBoost or your favorite Python library, you can extract the images from Earth Engine and then instead of sending them over to TensorFlow, use scikit-learn. One of the examples that I talked about in the plenary was something that I did earlier last week, which was just, scikit-learn is really great in how usable it is. It's how easy it is to get started. I pulled the data out and just threw it into the clustering algorithm locally. That doesn't scale across globally, but if you want a simple solution to get you started, it can be a nice way. So that's supported as well. Other questions?
Yeah.
Yes.
The question is about the product. So I know that Google, the GCP has the deep learning images. So I've deployed that before. So what's the difference between the deep learning images and the Vertex AI? Is there any additional features in the Vertex AI?
Do you want to just hear?
I'm not sure, actually.
Yeah. So deep learning images, the short story is that deep learning images at this point, I believe, have been integrated into Vertex AI. The history there is that they were part of Cloud AI Platform before Cloud AI Platform was retired. I don't want to say retired, but Cloud AI Platform, Vertex AI was announced as the sort of successor to Cloud AI Platform. And eventually, you could expect Cloud AI Platform to be deprecated. It's not deprecated yet. Those deep learning images are used for a couple of things. One is running sort of notebooks in sort of a development environment, and the other is sort of running training. Both of those experiences are now part of Vertex AI. Vertex AI now calls the notebook experience Vertex AI Notebooks. And I actually don't know what the deep learning containers for training are called right now, but that same functionality is available in Vertex. And if there's any more detail you want to talk about that, I'm happy to sort of talk on the break, like if there's a real specific case you want to chat about.
Yeah.
Other questions about machine learning?
Yeah.
All right. I think we're also happy to hang out here for the next 10 minutes and answer questions if you want to come up to the stage and talk about something that's particular to your organization, something you're looking to achieve. But aside from that, thank you so much for your time. We're really excited to have you here.